Hello dear students, welcome to mathematics class. In this class, let us discuss the examples on Cauchy's theorem. So here we know that for any closed curve C, integration over C f of z dz equal to 0. So that is the statement of the Cauchy's theorem, where f of z is a function of a complex variable and C is any closed curve. So here verify Cauchy's theorem for the function f of z equal to z square, where C is the square having the vertices 0, 0, 1, 0, 1, 1 and 0, 1. So first of all, let us draw the square having the vertices as 0, 0, 1, 0, 1, 1 and 0, 1. So now this is the square having these four as the vertices, and now we need to show that integration over C f of z dz equal to 0, where C is the curve OABC, right? So this is the closed curve C. So now the integral with respect to this curve C is equal to 0. So now here integration over C f of z dz. So let us consider that square as the four straight lines. So such that integration over OA and the function is z square dz plus. So now first line OA and then AB, BC, CO, and the function will be same on each and every line. And now we need to find all these four integrals, and finally we need to prove that the sum of all the four integrals is equal to 0. Now first consider the integral. Now consider integration over OA z square dz. So here this is the line OA. OA is nothing but x axis only, and we know that on x axis the value of y is equal to 0 and x varies from 0 to 1. So means to integrate we need to consider the limits of x from 0 to 1 and y equal to 0. So now along OA y is equal to 0, right? So if y is equal to 0, then it implies that dy is equal to 0 on differentiating both sides, and we know that z equal to x plus iy and dz equal to dx plus I dy. And now y is equal to 0, then z is equal to x and dz equal to dx, because dy is 0 and y is also 0. So therefore these two expression becomes z equal to x and dz equal to dx, and also x varies from 0 to 1. So therefore integration over OA z square dz is equal to integration over 0 to 1. We know that z equal to x, so therefore it is x square, then dz equal to dx. So now it is equal to x cube divided by 3 from 0 to 1, which is equal to 1 by 3. So it is the value of the first integral, that is integration of OA z square dz. Now the next line is AB, right? So this is the line AB. So here AB is parallel to y axis, means it is nothing but y axis only, and on y axis we know that, and here x is a constant function because 1 comma 0 1 comma 1, x is not changing, right? Only y is changing from 0 to 1. So means here on the line AB x equal to 1 and y varies from 0 to 1. So let us consider the next line, that is integration over AB z square dz. So here along AB x equal to 1, right? So this is a line AB where x is constant, so therefore x equal to 1. It implies dx is 0. So now z equal to x plus iy and dz equal to dx plus I dy. So here we know that x equal to 1 and dx equal to 0. So therefore z becomes 1 plus iy and dz equal to I dy because dx is 0 here. Then here y varies from 0 to 1. So therefore integration over AB z square dz is equal to 0 to 1. Z is what? 1 plus iy, that is 1 plus iy whole square, and dz is I dy. Now here I is constant, taking outside, then it is 0 to 1. Now let us expand this one, that is a square 1, b square is what? Iy whole square, and I square is minus 1. So therefore minus y plus 2iy into dy. Then this is equal to I into, now integrate this one, y minus y square by 2 plus 2i y square by 2 from 0 to 1. Now for upper limit, so sorry, it is y square and this is y cube by 3. Then I into, here 2 and 2 get cancelled. So for y equal to 1, this is 1 by 3 plus I. This is equal to I into 2 by 3 plus I, or which is equal to 2 by 3i minus 1, because I into 2 by 3, I into I is I square is minus 1. So it is the second one. Then let us consider the third one, that is integration over BC z square dz. Now here along BC, so here this is the line BC, so here this is parallel to x axis, means y is constant because y is equal to 1, here also y is 1, only x is changing from 0 to 1. So therefore along BC y is equal to 1. It implies dy equal to 0 because y is a constant one, and if you differentiate that y with respect to y, you will get 0, that dy equal to 0. And now z equal to x plus iy, dz equal to dx plus I dy. So therefore here z becomes 1 plus iy, sorry, x plus I, because x plus iy is there, so that becomes x plus I, since y is equal to 1, and dz equal to dx. And here x varies from 0 to 1. So therefore here integration over BC z square dz is equal to integration over 0 to 1. Here this is x plus I whole square into dx, because here z equal to x plus I and dz equal to dx. Then let us simplify this one. This is integration over 0 to 1 a plus b whole square, that is x square minus 1 plus 2xi into dx. This minus 1 is from I square. Then this is equal to x cube by 3 minus x plus 2I x square by 2 from 0 to 1. Then it is equal to 1 by 3 minus 1, so 2 to get cancelled, plus I for x equal to 1, and for x equal to 0 all the terms will get 0. Then this is equal to, so here this is minus 2 by 3 plus I, because 1 by 3 minus 1 is minus 2 by 3 and I as it is. And here the limits are from, we are treating the line BC means x must be varies from 1 to 0, but here we have considered 0 to 1 means the integral becomes negative, right? So minus minus minus, here also negative, minus of this one, which is equal to 2 by 3 minus I. So here we are considering the line BC. So BC means from this point to this one, it means from the limit must be equal to from 1 to 0, but here we have considered 0 to 1 means the sign of the integral becomes negative. So therefore the answer is 2 by 3 minus I. And the last one is the line CO. So here this is the line CO, and on this line y is equal to 0 and x varies from 1 to 0. Here also same, the integral will become negative if we consider the limits from 0 to 1. Now the next one is integration over CO z square dz. So now along CO y equal to 0, then dy is, sorry, here x is equal to 0, x equal to 0 and dx equal to 0, and y varies from 1 to 0. So now z equal to x plus iy, dz equal to dx plus I dy, and here z equal to 0 plus iy means that is I y, and dz equal to I dy, and y varies from 1 to 0. So therefore integration over CO z square dz equal to integration over 1 to 0. Then here z is iy whole square and I dy. So here I is constant, taking outside. Then let us change the limits as 0 to 1, then the integral becomes negative, and iy whole square is minus y square dy, because I square is minus 1, then now minus into minus becomes plus. So therefore I into 0 to 1 y square dy. that is I into here y cube by 3 from the limits 0 to 1, that is I into 1 by 3, or it is equal to I by 3. Now here we have evaluated all the 4 integrals. So now the first answer is 1 by 3, right? That is for the first one. Now let us evaluate this one, that is integration over c f of z dz, which is equal to integration over c z square dz. So here from equation 1 we know that OA z square dz, AB, BC and CO. So here we have evaluated all the 4 integrals separately, and now let us substitute the values of them. So here first one we know that the answer is 1 by 3, right? That is 1 by 3 plus the second one from AB. So here for the line AB the value of the integral is 2 by 3i minus 1. So therefore it is 2 by 3i minus 1. And for the line BC, this is the value for the line BC. The answer is 2 by 3 minus I. So plus 2 by 3 minus I, plus for the last line the value is I by 3. So therefore it is I by 3. And let us simplify this one. So here the LCM is 3 and the numerators becomes, this is 1 plus 2i minus 3 plus 2 minus 3i plus I, it is equal to, so here 1 plus 2, that becomes 3 and minus 3, so therefore get cancelled. Then 2i plus I, that is 3i minus 3i, so therefore that is also cancelled, which is equal to 0 by 3, that is equal to what? 0. So therefore integration over c z square dz is equal to 0. Hence Cauchy's theorem verified. So therefore for the square having the vertices 0, 0, 1, 0, 1, 1 and 0, 1, we have verified the Cauchy's theorem. Next example is verify Cauchy's theorem for f of z equal to z into e power minus z over the circle C such that mod z equal to 1. So here we need to show that integration over C z e power minus z dz equal to 0 to verify the Cauchy's theorem. So here the given circle is mod z equal to 1, means the center of the circle is 0 and the radius is 1. So here given that mod z equal to 1, it implies that z equal to e power I theta. So here because mod z minus a equal to r and z minus a is equal to r into e power I theta, which is the equation of the circle. So now here z equal to e power I theta, then dz equal to I into e power I theta d theta. So limits are from 0 to 2 pi for theta. Then integration over c z e power minus z dz is equal to 0 to 2 pi here z equal to e power I theta, then here e power minus z is there, that is e power minus e power I theta, because z equal to e power I theta. Then dz is I into e power I theta d theta. Then this is equal to, the I is constant taking outside, then 0 to 2 pi, here e power I theta, so let it be as it is, that is e power I theta, e power minus e power I theta, e power I theta into d theta. So now put t is equal to e power I theta, then dt becomes I into e power I theta d theta. So here we have substituted t equal to this e power I theta. So here whenever we are changing the variable, the limits also will get changed. So therefore here when theta equal to 0, t is equal to 1, because the theta equal to 0, that e power 0 and e power 0 is 1, and when theta is equal to 2 pi, t is equal to, so here e power I theta is equal to what? Cos theta plus I sin theta. Then theta equal to 2 pi means cos 2 pi plus I sin 2 pi. We know that cos 2 pi is 1 and sin 2 pi is 0. So therefore t becomes 1. So now here integration over c z e power minus z dz is equal to, so here e power I theta is t and the limits are from 1 to 1. So e power I theta is t and e power minus e power I theta is e power minus t, and e power I theta d theta into I is there, that is I into e power I theta d theta, which is equal to dt. Then so integration of this one is minus t e power minus t plus e power minus t by using integration by parts. So we get integration of this one as minus t e power minus t plus e power minus t from 1 to 1. So here it is equal to 0 because the upper and lower limits are same. So for upper limit minus lower limit, both the values will be same. So therefore the difference of them is equal to 0. So therefore here Cauchy's theorem verified. So it is the way to verify the Cauchy's theorem for any given function. Next example, evaluate integration over 0 to 2 plus I z bar whole square dz along the real line up to 2. Real line means it is x-axis, and vertically 2 plus I. So 2 plus I means here coordinates of this point is 2 comma 1, because it is a complex variable which is of the form x plus iy, that is x comma y. So therefore it is 2 comma 1. Now integration over c f of z dz. So first let us draw the curve as per the given conditions. So here along the real line up to 2 means we need to draw x-axis up to the point 2 means 2 comma 0, then vertically 2 comma 1. So it is the given curve, that is OA AB. So therefore integration over OA f of z dz plus integration over AB f of z dz. So and now consider this as equation number 1. So let us evaluate those two integrals separately. Now first consider integration over OA f of z dz, which is equal to integration over OA z bar whole square dz. So here along OA means along this line we know that y is equal to 0 and x varies from 0 to 2. Y equal to 0, dy is equal to 0. So we know that z equal to x plus iy, then z bar. So z bar becomes x minus iy. So but here y equal to 0, it implies z bar equal to x, and dz equal to dx plus I dy. So here dy is also 0, hence dz becomes dx, and x varies from 0 to 2. Therefore here integration over OA z bar whole square dz is equal to 0 to 2. Z bar is x, that is x square dx. Then this is x cube by 3 from 0 to 2, which is equal to 8 by 3. So that is the value of the first integral. And the second one is AB. So here consider integration over AB f of z dz, right? That is equal to what? Integration over AB z bar whole square dz. Now along AB, so this is the line AB. So on this line we can say that, so here along the line AB we can say that x is constant, that is x is not changing, means x equal to 2 only, but the y is changing from 0 to 1. So therefore x equal to 2 and dx equal to 0, and again z equal to x plus iy, z bar equal to x minus iy. So therefore here z bar equal to 2 minus iy, because x equal to 2, and dz is equal to dx plus I dy. So here dx equal to 0 means dz equal to I dy. So therefore here and here along AB y varies from 0 to 1. So then integration over AB z bar whole square dz equal to 0 to 1. Z bar is 2 minus iy whole square and dz is I dy. So I is constant, taking outside, then 0 to 1. Here a minus b whole square, that is a square plus b square, that b square is iy whole square and I square is minus 1, that is minus y square, minus 2ab, that becomes 4iy dy. Then this is I into, here this is 4y minus y cube by 3 minus 4i y square by 2 from 0 to 1. Now here this is equal to I into, for upper limit y, that is 4 minus 1 by 3 minus 4i by 2, because y equal to 1. Then simplifying this one, that is I into 4 minus 1 by 3, that is 11 by 3 minus I by 2, or by multiplying with I, that is 11 by 3i plus 1 by 2, because I into I becomes I square is minus 1, so already one negative is there, so that becomes plus 1 by 2, sorry, not 1 by 2, here this is 2i, plus 2 ones are 2 twos are, that becomes plus 2. So now from equation 1, integration over c f of z dz is equal to, so here, so answer for the first integral is 8 by 3 plus, here it is 11 by 3i plus 2, so here 8 by 3 plus 2, that becomes 14 by 3 plus 11 by 3 I, or it is equal to 1 by 3 into 14 plus 11 I, which is the value of the given integral.